Welcome students. In the last class we saw the notion of relations. Now, in this class we are going to study the new class of relations called as equivalence relation. In the last class when we finished, we defined the notion of what is known as a symmetric relation. Let us begin with the same definition. Let us begin with the definition of a symmetric relation. Let A be a non-empty set and let R be a relation from A to itself. We say that R is symmetric if the pair, if the ordered pair A comma B belongs to R implies the opposite pair B comma A is also in R. Let us also review the same example that we last class. Let us look at the same example. The set that we had was 1, 2, 3, 4 and 5. R is all those x comma y from A cross A with the condition that the difference between x and y is an odd number. We wrote the set R explicitly. Let us do it once again. Let us write this R again. R equal to, look at 1 comma 2, the difference between 1 and 2 is 1, which is an odd number. So, you have 1 2, well 1 comma 1, the difference is 0, therefore, 1 comma 1 does not appear, and 1 comma 3 the difference is 2, 1 comma 4 the difference is 3, therefore, it appears, 1 comma 5 does not appear because the difference is 4. Now, 2 comma 1 that is here because the difference is 1, 2 comma 2 the difference is 0, 2 comma 3 the difference is 1, 2 comma 4 here the difference is 2, 2 comma 5 the difference is 3. Next one 3 comma 1 the difference is 2, 3 comma 2 the difference is 1, 3 comma 4 and then 3 comma 5 the difference is 2. Now, let us go to 4, 4 comma 1 the difference is 3, 4 comma 2 the difference is 2, 4 comma 3, 4 comma 5 and then we will have 5 comma 1 the difference is 4, 5 comma 2 and 5 comma 4. These are the elements of R. If we look at this R, then it is clear. One thing that can be noted is the following. What is that one can notice? Whenever the pair A comma B is there, then the opposite pair B comma A is also there. For example, 1 comma 2 is there and similarly 2 comma 1. Similarly, again next one 1 comma 4 is there and you can notice that both 1 comma 4 as well as 4 comma 1 is there. Similarly, 1 comma 2 and 2 comma 1, 2 comma 3, 3 comma 2, 2 comma 5, 5 comma 2, 4 comma 5, 5 comma 4. So, this says that R is a symmetric relation. So, therefore, R is a symmetric relation. Let us look at one more example. Let A equal to 1, 2, 3, 4, 5 and 6. R is all those m n comma m from A cross A with the condition that n divides m. Right. What we have is all those pairs n comma m such that n divides m. Now, let us write down the set R explicitly. Now, 1 divides 1, therefore, you have this 1 1, 1 divides in fact all the numbers. So, you will have 1 is paired with all 1 4, 1 5, 1 6. Now, going next to the 2, you see that 2 does not divide 1, but 2 divides 2, but it does not divide 3, but it divides 4, it does not divide 5, but divides 6. Next to 3, 3 does not divide 1 or 2, but it divides itself. 3 does not divide 4 or 5, but rather divides 6. And then for 4 we have only 1 4 comma 4, and similarly you have 4 comma 5 and 5 comma 5 and 6 comma 6. These are the things that you have, right. These are the elements. Now, notice that you have 1 comma 2. So, what is that you will have to note? 1 comma 2 belongs to R, but the opposite pair 2 comma 1 does not belong to R. Similarly, you have this the pair 2 comma 6, this is in R, but the opposite pair 6 comma 2 is not in R. So, these two things say that R is not a symmetric relation. R is not a symmetric relation. Now, let us do one more example. Let A equal to 1, 2, 3, 4, 5, and let me choose x capital X as the power set of A. This consists of, so this is the set of all subsets of A. Define a relation R on X as follows. Two subsets A1 comma A2, the pair A1 comma A2, this is in R if A1 is contained in A2. For any two subsets A1 and A2 of A, we say that A1 is related to A2 or the pair A1 comma A2 is in R if A1 is contained in A2. So, one can notice the following, that singleton 2 is contained in A, and not only that, the other subset 2 comma 3, this is also contained in A. Further, one can notice that singleton 2 is contained in 2 comma 3, that implies that the pair singleton 2 comma singleton, so the two element set 2 comma 3, this pair is in R, right. You have this set in R, but on the other hand it is not true that 2 comma 3 is not contained in singleton 2, because 2 comma 3 has got two elements while singleton 2 has got just only one element. That means that the opposite pair 2 comma 3 comma singleton 2, this does not belong to R. Therefore, R is not symmetric. Now, let us go to the next concept. Let us define one more thing. Let A be a non-empty set and let R be a relation from A to itself. We say that R is reflexive if the pair A comma A belongs to R for all A in R. Let us look at the last example that we had. The last example is our set A is 1, 2, 3, 4, 5 and X is the power set of A. We defined R as the pairs A1 comma A2 in power set of A cross power set of A, with the condition that A1 is contained in A2. What is that we know is that every set is contained in itself, and therefore, if B contained in A, that will imply that the pair B comma B belongs to R. Therefore, what it says B comma B belongs to R, therefore, R is reflexive. Now, let us go back to the one of the examples that we did again. We had our A as 1, 2, 3, 4, 5 and our R is all those x comma y in A cross A, with the condition that x divides y. Now, in this example we wrote what R is explicitly just few minutes back. One can notice that 1 always divides 1, 2 always divides 2, 3 always divides 3, 4 divides 4 and similarly finally 5 divides 5, which means all this pair, this whole thing, this all these elements, this set is contained in R. That implies that R is reflexive. Let us look at one more example. Let us choose this one 1, 2, 3, 4 and then let us say that R equal to all those n comma m such that m equal to n square. First thing that you can notice that the pair 1 comma 1 is in R, because 1 is just the square of 1, but the pair 2 comma 2 does not belong to R, which implies that R is not reflexive. In the same example, one can also notice the following, that the pair 2 comma 4 belongs to R, but the opposite pair 4 comma 2 does not belong to R. So, this also says that R is not symmetric. Now, let us move on to the next definition. Let A be a non-empty set and let R be a relation from A to itself. We say that R is transitive if the following holds. Whenever the pairs A comma B and B comma C belongs to R, that implies these two together should imply that the pair A comma C is also in R. We want two pairs A comma B and B comma C. Notice that the first element of the second pair is same as the second element of the first pair. Whenever A comma B and B comma C are in R, that should imply that the pair A comma C is in R. Then we say that such a relation is transitive relation. Now, let us look at the examples that we just had. The first example that we had is A equal to 1, 2, 3, 4, 5, and then R is all those n comma m in A cross A, with the condition that n divides m. This is what we had. Now, notice the following. Let us increase the set a bit more, so that things will be clear. Let us increase the set. Notice that 2 comma 4, this is in R, and 4 comma 8, this is in R. Also, that 2 comma 8 is also in R, right. In fact, whenever n divides m and m divides k, these two statements together implies that n divides k, right. Therefore, R is transitive. Now, let us look at the other example that we had just few minutes back. A equal to 1, 2, 3, 4, 5, and x is the power set of A, and R is all those pairs A 1 comma A 2 in P of A cross P of A with the condition that A 1 is contained in A 2. We saw that this is reflexive, but not symmetric. Let us verify whether this is transitive or not. So, suppose A 1 comma A 2 belongs to R and A 2 comma A 3 belongs to R. Now, the first one A 1 comma A 2 belongs to R, that tells us that A 1 is contained in A 2. The second one A 2 comma A 3 belongs to R, that tells us that A 2 is contained in A 3. Therefore, what do we have? A 1 contained in A 2 and the other hand you have A 2 contained in A 3. Thus, these two containments together implies us that A 1 is contained in A 3. That implies, that is, what do we have? The pair A 1 comma A 3 belongs to R. Therefore, R is transitive. Let us look at the another example, the same thing that we had just few minutes back. Let us have A as 1, 2, 3, 4, 5 and R is all those n comma m with the condition that the difference between n and m is an odd number. Now, here suppose the pair n comma m is in R and m comma k, this is in R. Now, what can we say about n and k? This is what is the question. So, now let us look at some of the examples that we had. Now, let us look at this one. In this example, we have 1 comma 2, is this true? That is what we wanted, n comma n in R and m comma k in R. Does that imply that the pair n comma k is in R? This is what we wanted. Now, we know that n comma 1 comma 2 is in R and 2 comma 3 this is in R, because the difference between 1 and 2 is 1 and the difference between 2 and 3 is also 1, but the difference between 1 and 3 is 2. Therefore, this does not belong to R. Therefore, R is not transitive. Now, let us move on to the main thing that we wanted. The main thing, the title, as we mentioned in the beginning, that we are going to say about what are known as the equivalence relation, a relation R from a non-empty set A to itself is called an equivalence relation if 1 R is symmetric, 2 R is reflexive and finally, we have R is transitive. Whenever R is symmetric, reflexive and transitive, then we say that such a relation is an equivalence relation. Let us look at some examples. Let us look at A equal to 1 2 3 4 5 and then R as all those n comma m with the condition that n divides m. What is that we know? What we did is we in fact found that R is not symmetric. Second, R is reflexive. Third, R is transitive. These are the things that we noticed. So, the first one, R is not symmetric, that says that, so this implies that R is not an equivalence relation. Right. Let us move on to this next example that we had. We had A as 1 2 3 4 5 and then x as the power set of A, all subsets of A, and then we define R as pairs A 1 comma A 2 in P A cross P A with the condition that A 1 is contained in A 2. Here what we saw is that R is not symmetric. Second, well, R is reflexive. But R is not transitive. So, the first one R is transitive, right. These three things together. So, the first one and second one, these two says that, sorry, the first one says that R is not an equivalence relation. But now the question is, does there exist a relation which is an equivalence relation? Yes. Let us do one more example. Let us consider, let Z denote the set of all integers. So, define R as follows. Define the relation R on Z as follows. So, we say that the pair n comma m belongs to R if n is congruent to m modulo 9, right. What is that n congruent to m? That is the difference n minus m is divisible by 9. This difference should be divisible by. Now, let us see that this relation whatever we have defined, this is an equivalence relation. Now, first thing what you will have to see is that this is symmetric. Suppose n comma m belongs to R. That means what? That is n is congruent to m modulo 9. That is the difference n minus m is divisible by That is, what does this tell us? There exists an integer k such that n minus m is k times 9. So, what we have is n minus m is equal to k times 9. Let us write down n minus m is k times 9. That implies that m minus n is minus k times 9. That means what? M minus n, this difference is divisible by nine. That means m is congruent to n modulo 9. That means what is that we have? The pair m comma n is in R. Therefore, R is symmetric. Now, second one, let us verify whether R is reflexive or not. So, let n belong to Z, then notice that n minus n is 0, which I can also write it as 0 times 9. So, that implies that n is congruent to n modulo 9. That implies that the pair n comma n is in R, that is R is reflexive. Now, let us verify whether R is transitive or not. Let n comma m belong to R and m comma r belong to capital R. So, n comma the pair n comma m belongs to capital R, that says that implies that n minus m is n is congruent to m modulo 9. That implies that n minus m is divisible by 9. That implies that there exists an integer k in Z, there exists an integer k in Z such that n minus m is k times 9. Let us call this equation as 1. On the other hand, what we have is that the pair m comma r is in capital R. That implies that this is equivalent to saying that m is congruent to R modulo 9. That is equivalent to saying that the difference m minus r is divisible by 9. That implies that there exists an integer p in Z such that the difference m minus r is of the form p times 9. Fine. Now, what is that we wanted is the pair n minus r, whether the difference n minus r is congruent to 9 or not, or it is divisible by 9 or not. That is what we wanted. Let us call the last equation as 2. What is that we have? N minus m is equal to k times 9 and m minus r is equal to some s times 9, p times 9. In fact, these are the two things that we had. Fine. Now, with these two things, let us try to calculate n minus r, which is equal to n minus m plus m minus r equal to, let me put the first two things in a single bracket and the second and third in the other bracket. I am just adding and subtracting m. For the first one, we have n minus m, which is k times 9 plus m minus r, which is p times 9, which is equal to k plus p times 9. Now, k is an integer and p is also an integer, therefore, p k plus p is an integer. So, let me say that, note that k plus p is an integer. Therefore, n minus r, which is equal to k plus p times 9, implies, with k plus p an integer, therefore, that implies that n minus r is divisible by 9, that is n is congruent to r modulo 9, that implies that the pair n comma r belongs to capital R. So, thus we have shown that R is an symmetric, reflexive and a transitive relation. Therefore, R is an equivalence relation. And now, let us do one more example. This example is related to geometry. Let A be the collection of all. So, all those deltas, so with the condition that delta is a triangle in R 2 or a two dimensional triangle, right. What you have is a triangle in R 2. Now, let us define a relation on R equal to all those delta 1 pair delta 1 comma delta 2 in A cross A, with the condition that delta 1 is congruent to delta 2. It is clear from our elementary classes that first thing is that R is symmetric. Why is it symmetric? What we know is that if delta 1, if triangle delta 1 is congruent to delta 2, that implies that delta 2 is congruent to delta 1. Therefore, in fact, these two are equivalent ones, therefore, R is symmetric. And similarly, every triangle is congruent to itself. Every triangle is congruent to itself. That means what? R is reflexive. Now, the third one, transitivity. Suppose delta 1 comma delta 2 belongs to R and delta 2 comma delta 3, this pair also is in R. What we will have to show is that delta 1 delta 3 belongs to R. So, delta 1 comma delta 2 belongs to R, that implies that delta 1 is congruent to delta 2. Similarly, delta 2 comma delta 3 belongs to R implies delta 2 is congruent to delta 3, right. We have these two. So, now what does this say? Says that, so these two together. So, let me call the first one as 1 and the second one as 2, these two together. So, 1 and 2 implies that delta 1 is congruent to delta 3. So, that means that implies that the pair delta 1 comma delta 3 belongs to R. Therefore, R is an equivalence relation. Now, let us do one more similar example, which again comes from the geometry of the Euclidean plane or the two dimensional Euclidean geometry. Let A be the same set, all those delta such that delta is a two dimensional triangle or a triangle in R 2. Right, what you have is a two dimensional triangle. Fine. Now, let us define R as all those delta 1 comma delta 2 in A cross A with the condition that delta 1 is similar to delta 2. The triangle delta 1 is similar to the triangle delta 2. Now, it is the same proof as what we did for the previous one. One can show that R is an equivalence relation. Right. Same proof or same method as the previous example, as in the previous example. Now, let us do one more example. Let script A equal to all those A such with the condition that A is a finite set. This script A consists of all sets which are just finite sets. So, define R on script A as follows. So, A comma the pair A comma B belongs to R if the number of elements in A is equal to the number of elements in So, written in set theoretic form, R equal to all those pairs A comma B in script A cross script A with the condition that the number of elements in A is equal to the number of elements in B. Now, let us verify that this R is an equivalence relation. First one is R symmetric. So, let A comma B belong to capital R. What does that mean? By definition, this is same as saying that the number of elements of A is equal to number of elements of B, and this is equivalent to saying that the number of elements of B is equal to number of elements of A, and this implies that the pair B comma A is in R, and therefore, this says that therefore, R is symmetric. Now, for the second one, let us verify whether R is transitive. To verify whether R is transitive, so let A be a finite set. So, given a finite set, we know that the number of elements of A is equal to the number of elements of A. That implies that the pair A comma A is in R. Therefore, R is reflexive. And finally, the third one, let the pair A comma B belong to R and the pair B comma C belong to R. Now, the pair A comma B belongs to R, that implies that the number of elements in A is equal to the number of elements in B. Similarly, we have that the pair B comma C is in R, that implies that the number of elements of B is equal to number of elements of C. Let us mark these as 1 and 2. Therefore, by 1 and 2 we have number of elements of A equal to number of elements of C. So, these two together imply that R is transitive. So, thus R is symmetric, reflexive and transitive, thus R is an equivalence relation. Let us do one more example again from geometry. Let A equal to the plane R2 and minus the origin. I am just removing the origin from the plane R2, which is in general called as the punctured plane. Let us consider the punctured plane. With this punctured plane, let us define R as follows: R equal to, I will say that the pair x 1 y 1 is related to x 2 y 2, or the pair x 1 comma y 1 is related to x 2 comma y 2 belong, which is in A cross A, if the condition that there exists a non-zero scalar lambda in R such that x 1 comma y 1 is equal to lambda times x 2 comma y 2. Now, let us verify that this R is an equivalence relation. So, first one, let x 1 comma y 1 comma x 2 comma y 2 belong to capital R. That implies that there exists a non-zero real number such that x 1 comma y 1 is equal to lambda times x 2 comma y 2. Now, since lambda is non-zero, lambda is invertible, that means 1 by lambda makes sense. So, therefore, that implies that 1 by lambda times x 1 comma y 1 is equal to x 2 comma y 2. So, this is equivalent to saying that x 2 comma y 2 is equal to 1 by lambda times x 1 comma y 1. That implies that this pair x 2 comma y 2 comma x 1 comma y 1, this is in R. therefore, R is symmetric. Now, let us verify whether this R is reflexive or not. So, let x1 comma y1 belong to A. Now, what we know is that for any x1 comma y1, x1 comma y1 is equal to 1 times x1 comma y1, and since 1 is a non-zero scalar, that implies that this pair x1 comma y1 comma x1 comma y1, this is in R. Therefore, R is reflexive. Now, finally, let us verify whether this R is transitive or not. Third one, let the pairs x1 comma y1 comma x2 comma y2 belong to R, and the pairs x2 comma y2 comma x3 comma y3 belong to R. Now, the pair x1 comma y1 comma x2 comma y2, this belongs to R, implies there exists a non-zero real number such that the pair x1 comma y1 is lambda times x2 comma y2. Let me call this as 1. Now, similarly, the pairs x2 comma y2 comma x3 comma y3, this is in R, implies there exists a non-zero scalar beta in R such that x2 comma y2 is beta times x3 comma y3. Let me call this equation as 2. Now, what I am going to do is substitute 2 in 1 to get what we wanted. Let us do that. Substituting two in 1, we get x1 comma y1, this is lambda times x2 comma y2, but then when I substitute for x2 comma y2, I get lambda times beta times x3 comma y3. But since lambda and beta both are non-zero real numbers, that implies that this lambda beta is a non-zero real number. That implies that the pair x1 comma y1 comma x3 comma y3, this is in R. Therefore, R is transitive. Thus, we have shown that R is symmetric, reflexive and transitive. Thus, R is an equivalence relation. So, in the next class we will do the proof of this and some more properties of these equivalence classes, and then we will try to define the notion of what is known as their function. Thank you all.